So in this session, Dr. Mahendra Kumar sir is being with us. Before start the session, let me introduce Dr. Mahendra Kumar. So Dr. Mahendra Kumar currently working as an assistant professor, instrumentation and control engineering department, and associate faculty at Center of Energy and Environment, Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. Before uh, Dr. Mahendra Kumar worked as an assistant professor, HOD Biomedical Engineering Department and R&D coordinator at Faculty of Engineering and Technology, Datta Mega Institute of Medical Science, deemed to be University, Swangi Verde, India. So Dr. Mahendra Kumar have done PhD from Department of Electrical Engineering, Indian Institute of Technology, Roorkee. Dr. Mahendra Kumar have obtained MTech and BTech from State Government Rajasthan Technical University Kota in 2012 and 2010. Dr. Kumar have around 5 years of teaching and research experience. Besides, Dr. Kumar have awarded by Gold Medal for Excellence in MTech by Rajasthan Technical University Kota. From research point of view, Dr. Mahendra Kumar have published research work in IEEE Transaction, IIT, Taylor and Francis, and Springer Journal. Dr. Kumar research area is to design PID and PIDA controllers for time-delayed and uncertain systems, polynomial control design, robust and non-fragile control design, and their applications in aerodynamical systems, in power system operation control, DC-DC converter. So thank you, Dr. Mahendra Kumar sir, for coming and accepting our invitation. So today is the last day of this active which is organized by E&ICT MNIT Jaipur. So now I welcome to Dr. Mahendra Kumar sir again. So now to please take the session.
Okay. Yes, thank you, Dr. Surendran sir, for giving nice introduction to participants and it's like sir given a lot of things tell me about. So my area is regarding control, but from application perspective, like I apply in the power system, power electronics, and some more areas like robotics. But RL, how to we can interface with it? So we can discuss with the RL here and its application in the this domain. Okay, so I start sharing my PPT first, so then we can discuss. So I think these PPTs are visible, I think, huh? Sir, answer.
Hello, yes sir, visible sir.
Yeah, okay. Okay, thank you, sir. So, so today, this is a workshop regarding the E and ICT sponsor online FDP on the deep learning. So, as per the deep learning, we are discussing our reinforcement learning, and it's mainly application and reinforcement learning based control design, and its application in the power system and power electronics. Okay, like power electronics, basically in the power converters. So we can discuss some of the things here. Okay, so let's we start with the some basic control perspective first, because my whole things about the control system. So first we can go some motivation regarding the control, then some problem issues with the conventional control, then we can go with the reinforcement learning. Okay, so here in the slides it's visible, I think. So in the motivation perspective, we have the each and everything here and there in our nearby. Like robotics, we have things, power system, everyone access electricity at home. Okay, electrical supply, and the biomedical robotics, missile guidance, agriculture, and each and every perspective, every domain needs the your control system and control loops to get the desire your response. Okay, and your specific output with the desired quantity. So we need some control loops. So what are the issues with the key problems? Okay, so in the system we have some disturbances like internal or external. system have the some problem in internally whenever and some external like changes in the due to the environment and due to the some other things, noises in the system, maybe it gets through the maybe sometimes in the sensors measurement also. Parametric uncertainties, non-linearities, cyber attacks in coming era and in the currently the cyber attacks is also one of the big problem. Time delay, time varying disturbances, stochastic nature of the lower demand and intermittent nature of renewable. Like we are in the era of the smart grid and the addition integration of the renewable in more and more in the power system power grid. So there is a issue with the renewable intermittency also. And these are the problems with the system, but the key issues like the what we are facing in the when we are designing our controller. One is concerned is the system stability, fragility, robustness, resilience, adaptability, and intelligence. So all are the parameters we need to maybe come up with the control design. But we are not come with all the parameters key issues in the single one. Okay, but in case of the AI based control design have the some adaptability, intelligence, stability, constant resiliency. So somehow most of the content and most of the issues we can resolve with the AI-based control design. So there is a one of the map I have mentioned here, the like solution lot of control theory, mathematics based and the AI-based optimal controls, adaptive controls, conventional control, modern control. Lot of algorithm has developed in the literature also. Okay, so the whenever we start about the discussion about the control, then first controller is come in our mind is like PID control. Okay, so PID control is nothing but it is the base of the control design in the industry, process industry, chemical industry, power industry, everywhere it is mainly dominated in the as a control loop. But in the last from 20 years, like we are going with the some modern controls also. So MPC is also one of the modern predictive control is also dominating as a hardware perspective, and another like fuzzy based control design, ANN based control design also coming in the research, but in the from hardware in the industry perspective, most of things are in the only research, not in the practical perspective in the industry application. So PID is the widely used in the industry. Okay, so PID have the basically improve the stability and damping of the control system as our requirement, as our desirability. So there is a it have the three terms, three term control. We sometimes call it three term control also. So KP, KI, KD are the three gains or three terms of the PID. So PID actually works in the uh, whatever the transfer function we have in the system. Okay, because we are here maybe the engineering like participants, so people are understand the transfer functions or like some key terms of the control system or so the some of the limitations of the PID have the like it can't handle the large time delay in the system. Sometimes like time varying disturbances we are discussing about the some renewable also. So there is some issues with the PID. Okay, and the design of the higher order systems because we have the industry, we have the thousands number of order of the system. So if we go with the like analytical way, we can't design the PID. But in case of the we need to reduce the system order and we go with the some reduction of the order, then we are designing the PID controller. Okay, and the another task is the main task is the tuning of the PID controller. So main issue with the RLE we can discuss about the tuning of the PID parameters. Okay, now so one of the example we have considered that here we have the one of the third order system with the integrating type system, and we have the root locus plot for the this particular plant equation 2, and we have designed this PID controller for this one also, and we are getting the control loop gain, loop transfer function like equation 4 third PID, and we have the root locus for the loop gain as a figure 4. But the we are observed that the system is unstable and behavior of the control system is a unstable way. Okay, so here actually I worked during my PhD, and afterward onwards I am working on the PIDA controller. It is just extension of the PID, and double derivative or restoration term is added. So it is mainly used in the derivative terms in the inverse control, or maybe we can go with the like robotics things. okay, or maybe space application is wide application of the derivative terms for the PIDA controllers. Okay, so it has a one more. It is a 4-term control, and it here we add the one more element like KA acceleration gain. So it is a fourth order system. It is a like first order system, but it have the 3 zeros. So now we have got their structure is given in the equation 5, and it is continuously this time like in the 5 to 10 years people are working with the PIDA also, and more dominantly working in the PIDA also, to handle out the isolation problems also. Okay, now so we designed this PIDA controller for the similar equation 2 our plan, and we are getting the system is somehow most of the gain the controller is stable. Okay, this plant is stable response we get. So in such a way, if you extend our structure of the controller, or maybe we tune the properly system, control your controller, then you get the somehow your desired response. Okay, so some of the research gaps and problems are available in the literature. So we are discussing about the tuning of the PID or PIDA controller. So I will discuss about the PIDA and some basic algorithm, analytical algorithm, coefficient diagram method, or internal model control approaches. So little bit we can go through fastly. Okay, so here like first, if you go with the, we are going with the like coefficient diagram method. So uh, okay, so its application in the LFC or AGC for the Indian power system perspective. So our main target in the power system, we are adding the like renewable more and more dominant integration of the renewable. So as we need to control the voltage and frequency in the power system. Okay, so there is a one of the main challenges is the frequency control also, and most of the times power plant outage is held due to the your frequency. If you are not properly controlling your frequency in the system. Okay, so frequency control is not in the India before 2018, and initially started with the pilot project in 2018, and now we are maybe in the coming years we have the whole power plants with the frequency control also. Okay, so it is one of the application where we are going with the control now. So CDM I just discussed. CDM is nothing but coefficient diagram method, and it's designing perspective in the power converters. So CDM is basically introduced by the S. Manabe. It is a mathematical polynomial control design, and it has the better reference tracking and disturbance rejection capabilities. So here we have the some general transfer function of the system, nth order system, like equation 7. Okay, and we have the controller transfer function like here similar nth order, but as we know the integral control is the more important in the PID regarding the reference tracking, or maybe with steady state error less, or maybe the minimum steady state error. So we are going with the L naught is the 0. Okay, we can put the L naught is 0, so we can get the integral portion or integral effect in the controller design. Okay, so here we form the one of the target closed loop characteristic polynomial like equation 9, and we need to get the DC, and NCS is nothing but the controller parameters, controller transfer function, numerator and denominator. So we need to unknown parameters of the that controller. Okay, this controller. So how do we can get these things? Okay, so here we consider one of the desired closed loop characteristic polynomial in the equation 10 is given like that, and we can compare the equation 9 or 10, then we can get our unknown parameters of the controller. Okay, like KPK, KD or KA, like. So how do we can get this parameter, and how do we can frame the desired closed loop characteristic polynomial? So like we have the one of the like definition for characteristic ratio. Characteristic ratio, generalized time constant are the key elements in the coefficient diagram method. So these parameters we have defined like that. Or PI is nothing but the coefficient of the desired characteristic polynomial. Okay, now so we got the tau in that way, or maybe the PI in terms of the gamma. So if you know the value of the tau and the gamma, and then we can get the your characteristic polynomial, like your coefficient of the desired closed loop characteristic polynomial. Okay, now so in such a way we have got the this relation as equation 14, and we have the some constraint on the stability. How do we select the gamma's value? So this is equation 15 and 16. If we consider this equation and satisfy this constraint, then the whatever the value we consider for the design of the desired characteristic polynomial, it is up to with this stable portion. Okay, so we can compare the desired or target characteristic polynomial, and we are getting the unknown values of the like our controller parameters. Okay, so there is a lot of like improvement in the continuously in the theory, and then I have considered this design for the non-minimum phase system. So here we consider the non-minimum phase system with the time delay or unstable way. So I have first for the Paddy approximation, then we can get the equation 27, and we consider gamma 1, gamma 2, and gamma 3 values here in the range with the satisfy the constraint. And if we consider like settling time here 3 seconds, so we are getting the tau is 1.2. So in such a way we get the controller transfer function and the pre-filter transfer function for the controller design like here. So we get our response like reference tracking and the disturbance rejection. Okay, so from the perspective of the CDM, like a polygon or the 2-degree freedom very similar one. So we are getting the like polygon is have the better response as compared to Exist, Jung, and Paddy and Maji as the reference tracking and also in the disturbance rejection. So here the coefficient, the analytical way is given the us good responses as our desirability, and in case of the quantitative way also we can measure that based on the integral performance parameters also and controller energy based. So we are observed that the proposed one is have the good one response, but in case of reference a little bit control energy is more, but in case of disturbance rejection this control energy very less as compared to existing other control perspective. Okay, so and another case of the stability, we are getting the good stability and the relationship between the robustness and stability, so and performance also. Okay, which is we can observe from the maximum sensitivity coefficient. Okay, so design one polygon is provide the better response, but what are the issues with that here? Gamma selection of the gamma values, how do you can select the gamma values, gamma and tau value? Okay, for this one we have a lot of optimization approaches. Okay, algorithm is available, nature inspired algorithm or the conventional optimization algorithm. You can apply and you can get this parameter, but it is not we are getting the better responses. Sometimes it is based on the your algorithm. Some one algorithm given the better response, another not. Okay, so this just like the one of the theorem is no free lunch theorem. So optimization algorithm have the always issue with the no free lunch best theorem constraint. Okay, so in such a way uh, from application perspective, like DC-DC buck converter, we extend the this theoretical concept. Okay, so what happening? We have considered like the non-ideal DC-DC buck converter. These are the parameters of this one. So this is your voltage. Okay, input now, and this is output voltage. So and these are the your switch, your diode, inductor, and capacitor, and resistant load. Okay. So mainly issue with the buck converter is the load changes continuously. If load changing, then the issue with the output voltage. Okay. So we have considered here 12 to 15 volt input voltage, and we have the output voltage like the 8 volts. So that's why it is a buck converter. So whatever the input, it is less than as the input is higher than as compared to your output. Okay. So we have get the transfer function for this one based on the parameter we consider from table. We get the GS like that, equation 31, and we consider the gamma 1, gamma 2, gamma 3, and the cycling time is the 2 milliseconds. So based on tau is 18 to 4, and we are getting the controller parameters also. So in such a case, we get our response. In the different case study we have considered here. First case is nominal case, second is the sudden change in the input, sudden change in the reference voltage, sudden change in the load, and last one is the parameter uncertainty in the inductor or capacitor. Okay, so in all the conditions, like all voltage we have changed from the 4 to 8 volt continuously, one unit step change. So we are getting the better one response as compared to IMC PID control with the polygon. Now in the from in a quantitative way also we can get this rise time in the better way, and from the total variation is the also control perspective. Your control is how effective the TV is less than. Okay, less TV is maybe good your control design. So polygon has the less TV, it means it a good one as compared to other one. Okay, MS is also a stability constraint. Now so responses we have changed here from the input voltage. Okay, sudden change in supply voltage. So we have changed here 12 to 11 and 11 to 12, and here is 12 to 13 and 13 to 12. Then we are getting our response in the output in the without any effect much more. Okay, now like reference change, it is also reference we have changed from the 8 to 6 and 6 to 8 to 10, then we are getting our reference tracking properly with this control. Now sudden change in the load, if sudden change in the load, it is also one of the issue. So 20 to 10 ohm and 10 to 20 ohm, then we are getting our response in a up to mark with the load change also. So these are the responses we are getting with the polycon. Now primary uncertainty due to the life age. Okay, aging with the aging concern, the capacitor inductor have the and due to the heating there is issues. So temperature issues. So it is there is some parametric values that change. Okay. Now so that's why we consider plus minus changes in the inductor and capacitor. And based on the tolerance, okay, that's based on the tolerance. Tight tolerance have the high cost and less tolerance have the less cost. Okay, so if you go with the more like 10% 20% tolerance, then it is a less costly components, and your system cost is also less. Okay, converter cost. Okay, so in such a case we get the minus 10% change in the L or plus 10% change in the L. We get the response proper one with the polycon, and similar one in the change in the capacitance plus minus 20%. Then we also get the similar better response as compared to existing one approaches. From the theoretical from hardware perspective, we have the hardware results also. So we change the our reference. First we are getting the output 10 at the 8 volt with respect to your input. Okay, now it is nominal condition. Next sudden change in the input voltage, so we have changed the sudden input in the voltages, but the our response is a always our similar one. Okay, from 12 to 11 and 11 to 12, or maybe 12 to 13, 13 to 12. In that case the output voltage is not changed. Now in case of the reference, definitely it changed, output is changed with the reference. So 8 to 6, so here 8 to 6, and then 6 to 8 again. Okay, 8 to 10 and 10 to 8 again. So with our proposed one, it's also we are tracking proper way. Okay, now so these are the some with the load also we are getting the after some sudden then remove it, then we are getting the our reference proper tracking. So from the simulation and hardware results, we predict that the the analytical way is give the responses in better way, but sometimes the trial or error, the parameters we are selecting based on trial error, if we have the some proper approach, then it's too much good to we are getting our response in proper way or based on the real time also. So in such a way we consider like RL reinforcement learning also based on the based on the awards, it gives the real time responses, and it tune the parameters gamma 1 gamma 2 in the proper way, so, then we can get the proper responses. Okay, so we are coming with the RL. So this is a whole regarding the motivation about the control and where we apply the RL in such a way. That's why I discussed the CDM. Okay, so like challenges with conventional control. So PID control limitation cannot handle the nonlinear and constant system, require manual tuning, not adaptive to dynamic environment. So to make the system adaptive and dynamic, a dynamic environment, we are adding the RL with the PID control. Then we are somehow handle out the issues of the adaptiveness. Now, robust control issues also. We have the in the robust control, we have the H infinity controller. So H infinity controllers have the issues like higher order systems. Okay, so higher orders constraint, it's not feasible to hardware realization. So there is a issue. So design for the worst case scenario can be conservative. Generally, we think about that the our worst case is worst case we consider some parametric uncertainty in the system, and we consider that this particular plant, if we control it, we have the multiple you are think about the time interval plants time interval system. In the time interval system, some particular values the system may be the more at the unstable way, or maybe the more at the worst responses. So we consider in the worst case scenario the worst case plant. Okay, transfer function. Okay, so it is conservative issues. Okay, difficult to implement for highly complex and the uncertain system. So these are the some issues with the PID and the robust control issues. So need to next generation control like the RL based control. So next generation control system like RL based control design refers to advanced control mechanism that leverage the cutting edge technologies such as the AI, machine learning and optimization algorithm to enhance the automation, efficiency and adaptability in the various industries. So playing a crucial role in the modern engineering by improving the performance, minimizing human intervention and the enabling real-time decision making also. So like I mentioned it, like in the real-time industry, like analytically we design the PID once, And if there is a more maybe the changes in the we are not getting response, then we can again go with the offline and we are tuning the parameter, or maybe online trial or error we can change it. But if you don't want to go with the trial or error, or we don't want to manual changes in the parameters, then we can go with the real time system, and we can edit with the like RL base, or maybe the with the modern approaches like RL, next generation control. Okay, so next generation control, advanced control technique beyond the classical PID, handles non-linear constant or adaptive systems, like RL based control. And application we discuss of power system and some power electronics concept. So this is the RL. So is we are going with the some fundamentals, not more details in the like mathematics or more deep. So we have considered here RL has the some particular functioning, like it has the environment. Environment is nothing but your system. Okay, your system, your plant, or somehow people consider the controller also inbuilt with the environment also. So you can consider plant as an environment, or maybe the controller with the controller plus plant as an environment. Okay, no issue. Then we have the some rewards here. One of the terms is reward, and this so it face the states, and go with the agents. Agents give the some action to system. Okay, this is process continuously is ongoing. Okay, so reward based things is too important in the RL. What happening, like RL reinforcement learning is nothing but we have the three types of learning in the ANN. Like first is supervised learning, unsupervised learning, and reinforcement learning. Somehow one more is a semi supervised learning, but we are considering here the reinforcement learning. Here we learn from ourselves based on the task. What task we have done, it is select based on the our selection, and based on the your awards. So awards is good. Okay, you get the more, gaining the more awards, then you are moving in the forward direction. If your awards not in the negative way, then you try the with the some another way. Okay, your selection is not proper. Okay, so there is a one constraint in the RL is the selection of the rewards. Okay, how do you select the reward? How do you give the award to your your function, whatever objective function you define, how to it will update based on the award. Okay, so there is a challenges with the here also RL is the reward selection or your action. Okay, what reward based action also in the environment. Okay, so here we have considered one of the scenario like that, environment is just like girl in the angry way, and agent just like the dog. Okay, so if environment like agent gives some action, okay, based on the action, environments give some rewards based on some particular psychological perspective, or maybe the based on the their thinking, and based on the it also provides the feedback to agent. Okay, so if there is agent is walk, okay, then the environment have the some stick in hand, and she want to hit the dog, then it is just like the reward to dog. And if dog is stopped, then there is no issue. If not stopped, then the maybe she will hit the dog. Okay, so it is a continuous process. If dog is out maybe from their place, then no issue. Otherwise, and maybe dog is stopped, then the environment, maybe the girls is maybe happy and go for their work. Okay, so there is a one of the action, whatever the action you provide, based on this action you get the some rewards. Okay, so there is a learning, reinforcement learning is a main concept based with the rewards. Okay, what rewards you are getting, positive or negative, based on your action. Okay, so here one of the another constant we can consider, like we action left, down, and up and right, and probability 0.4, 0.1, 0.2, 0.3. So environment is our earth, and action, and based on this earth state or observation, we are getting the movement of the agent, like want to maximize reward. So this particular agent want to maximize the reward, so we are moving in the left side more, or maybe left or right, not up and down. So based on the rewards, we are getting our desired response. Another concept, and maybe we can go with another scenario, like one of the like children in the family. Okay, it is agent, and there is the environment. Okay, family members, mother as the environment, and another, like here we have the task. He agent need to choose what action, like, so it get the reward based on the action. So if a child, agent select the glass. Okay, uh, so there is a issue. It is not good for him and him or her. and if select the milk bottle, then it's a good one. Okay, so based on this scenario, we can think from here. If it is select the glass bottle, glass, okay, and so then it is punishable. It's seen that agent seen that if someone select the glass, okay, then it is punishment to the particular candidate or particular agent. Okay, now if we select the bottle, water bottle, then it get the reward. So based on the trial or error, and based on the your selection, you are getting the your best output or best rewards. So if you get the more and more rewards, then you are moving in the forward better way, and you are getting the desired response. Okay, now another constraint, why RL in the control design. So no need for the accurate system models. Generally, in the analytical way, we need to our transfer function or particular model. So we design our PID controller. Like I already mentioned you, like we have the second order system, then we can design analytically properly PID controller. Okay, if we don't have the second order system, we have the third order, then we need to go with the reduced one. Okay, but in case of the RL, we are not required the accurate model of the system. Adaptation to changing the environment. Whatever the environment you have, it will adaptable. So RL enables controllers to adjust to change in the environment or system without human intervention. So sometimes it is an intelligent one. Based on the rewards, based on the feedback, it updates itself and give the particular action to your system. Okay, so you are no need of the human intervention in between here. With the emergency situation is a different one, but in case of the in normal condition, in the some disturbances condition, there is no use, no need of the human intervention. Another case, changes in the environment sometimes. Okay, like parameters changing. Okay, somehow some values are changing and system parametric uncertainty or some disturbance may be more, then the RL controller will handle it. It's adaptively. Okay, now optimization of the complex objective. RL allows the design of the control system to optimize for long term and complex objective. Whatever the objective function you define it, and you get the some objective to satisfy some objective, it will handle out based on the RL algorithm or maybe policies. Now end-to-end learning, here we are in the environment. So we are learning. Our controller is learned based on the environment changes or maybe the disturbance in the environment, and it will give the response to the environment. So as it get the reward, it gives the action. So action and reward is continuously in a function. Scalability and generalization. If we design our RL for the particular some system, then we can scalable it for the larger one or maybe the more like scalability. So we have the one module, then we can design for the multiple modules also. So scalability and generalize. So RL can be scaled to higher dimension problem. Once trained RL based controller can generalize to the new unseen situation as long as the underlying environment shares by the key characteristic with the training condition. So whatever condition you have given during the training, based on that and some of the unseen conditions also, it will give you response. Like in the last example, we consider like glass condition. Okay, so if you touch the glass or you are play with the glass, then you get the punishment. Okay, so whenever you, yeah, there is a one concern for children. Okay, he or she seen, but there is another condition. If there is he or she seen the glass in some another condition also, they will not go with that. Okay, so unseen conditions also they will consider that it is punishable, so that's why they are not going with the glass portion. Okay, now so some comparison or somehow we can improve our existing algorithm, control algorithm based on the RL or RL role in the betterment. Okay, so control method, their strength, weakness, and the RL roles in the betterment. So first PID, it's simple, real time, low computational cost, definitely. PID is available and easily we can design for the any type of system. Okay, there is a main issue with the tuning complexity and struggles with the non-linearity, which is we earlier discussed. Now, so RL can optimize the PID parameters, adapt to changing condition, and enhance the performance. So if you tune the PID parameters with the RL, okay, properly, then there is a not issue with the non-linearities or maybe changing condition. Now, next one is the MPC. MPC is nothing but a model predictive control. It is also based on the mathematics and based on the optimization. Okay, so here there is a task with the optimization. Okay, if you not properly optimize the things, the your function, then you are not getting your response. Constraint you need to satisfy. So strength is handle the constraint multivariable system. Okay, there is a lot of you can handle the constraint and multiple variable, but there is computational expense because there is a more constraint, then it will take the more time. Okay, and model dependent. Model predictive control definitely based on the model. If you not have the model, then it will not feasible to apply the MPC model predictive control. So how to RL is maybe do the better one betterment for the MPC. RL can improve the model accuracy, optimize the control decision, and reduce the computational load. Whatever the optimization constraint, it is run by the RL in a very efficient way or fastly. Now, H infinity control, like robust control, we I also discussed in the before. So H infinity is nothing but there. It is robust against the disturbances, model uncertainties. Like we have the some parametric uncertainty, then the robust H infinity is good one. But there is a issue with the high complexity. Depends on the accurate modeling. If your system is not modeled accurately, then H infinity response is not you are getting the proper outputs. So how RL maybe do betterment for it? RL can refine the robustness parameters and handle the unknown disturbances more efficiently. So it is handle out the robustness parameters, whatever the constraint you are given, like maximum sensitivity, consider sensitivity constraint, you can solve it with the RL in better way. Okay, now it sliding mode control SMC. It is robust in fast response you are getting, but there is a issue with the chattering complexity. There is a issue with the chattering and complexity in the SMC design. Okay, so there is a more maybe more SMC design and more variant is come in the like literature, but the chattering issues and it's somehow there. And the constraint is that if you go with the more mathematics, then it is too tough to understand, and for industry persons who are not more feasible with the SMC. Okay, now so RL can how do RL is do betterment for it? RL can reduce the chattering, optimize sliding surface, and handle the non-linearities. Okay, now it is nothing but the event triggered control, efficient response use. Because event trigger control, when you have some disturbance, then controller is act in a better way. Okay, otherwise there is a normal functioning with the bias one, but whenever you get some disturbance, then the controller is act, then it means it the whatever the resources on the controller energy, it use the very less way. Okay, so efficient resource use, ideal for distributed system. Now weakness is potential loss of the precision. Because what happening, the controller is act on the when you get the disturbances. Okay, somehow some disturbances maybe in the system and some other issues, then it can't get, you are not get the proper response in the ETC. So RL can optimize the event trigger threshold. Definitely it will improve the where you need to give your you start your controller. Okay, based on the disturbance, improve the trade-off between the efficiency and performance. What is the efficiency and performance? It is balance between the efficiency and performance, controller efficiency or performance control system. ADRC is nothing but the active disturbance rejection control. ADRC is nothing but the ADRC. So it is also one of the feasible or extension of the PID. And here we have the some like extended state observer, so it gives you better feedback in case of the like you are working with the real time also. You can do it with the ADRC. So robust load disturbances and model free. Here we are not read the require the actual model of the system. We know the system model, then we can design the ADRC also. Complex observer, there is an issue with the ESO observer designing. Okay, so if you are expert in the mathematics little bit and you know the observer concept properly, then you can go with the ADRC also. Now, how to RL is maybe do betterment in the ADRC. RL can improve the disturbance rejection, optimize the observer, and adapt to the system dynamic. There is a one concern like in the ADRC, we have the frequency like bandwidth. Okay, controller bandwidth or controller frequency crossover, gain crossover frequency, and here is also we have the like observer frequency. Okay, or observer bandwidth. So those parameter, how to we can select it? Okay, what will be the constraint on the bandwidth, which is we required to select based on the RL. If you select in better way, then the DRC do the wonders in the control design. Now another things, ESC is nothing but the extreme seek control. Okay, so extreme seeking control, simple, model free, optimized performance, but there is a issue with the slow convergence. It takes the time. and limited to single objective. It work only for single objective. If you go with the multiple, then there is an issue. So RL can accelerate the convergence. RL will help to improve the convergence, handle multi-objective optimization, and adapt the perturbation strategies. Whatever the perturbation condition you consider, it will adapt you with the extreme seeking control. So whatever the existing system we have the existing system, we are do the betterment based on the RL, and we can involve the or integrate the RL in the existing one. Then we are getting the our proper response. Because we know that we can't change the hardware, whatever existing hardware in the industry, we can not directly change it. We need to improve it, and we can integrate the some more better modern things with it. Then we can get the our responses. Okay, so here the RL importance in the existing one. So it have the model based, model free things. So model free RL, and so it is a real experience based things, and learning from the real experience and based on the policy and get the some values. Okay, now model based, there we have the some model, we planned it and get this our based on the value or policy. Okay, so model based or model free, we have the some model, then we can design model free. There is, we are not requiring like black box, we can go with the black box things, model free RL. So some of the algorithms available in the literature, like now control methods, some and some strength, weakness, and the RL roles and use. Okay, so proximal policy optimization (PPO), DDPG, and SAC, and Q learning. Q learning go with the discrete one, and another three go with the continuous control task. Okay, so generally DDPG is worked in the like most of the papers you've seen. Then the SAC, soft actor critics, and the DDPG is mostly used. Okay, now so proximal is also, so proximal policy optimization (PPO). It's strength, high sample efficiency, stable and easy to tune. This PPO is easy to tune and often works well in the continuous action spaces. Okay, so issues with that may struggle with a very complex or high dimensional environment. If you have the high dimensional environment, then there is issue with the PPO and require careful tuning of the hyper parameters. Some parameters is here. If you it's required the careful tuning, maybe selection of the parameters is better way. Okay, now so RLPPO improves the stability and efficiency in continuous control problem while avoiding the large policy. So it how we use the PPO for the RL as a policy updation. Now DDPG is a deep deterministic policy gradient DDPG. So it is strength is suitable continuous action space, handle the high dimensional state spaces well. Like issue with the PPO, it's handled in the DDPG. Now weakness is sensitive to hyperparameter selection, prone to overfitting. Here is the issue with the overfitting. Okay, to consider, you note underfitting and overfitting. Or overfitting is also issue with the selection of the parameters. Now struggle with the exploration. It is not explore with the more and more space. So there, that's why it is go with the overfitting constraint. Now so DDPG is effective in the environment requiring the precise control, continuous action control, but but may need extensive fine tuning. So we can go with the DDPG, but it's good one as compared to PPO. But here we need to fine tuning with the algorithm. Okay, now SEC, soft actor critics SEC. So highly simple, highly sample efficient, robust to noise and reverse scaling, well suited for the continuous control task. So that's why I mentioned that SEC is also very popular in the research and application applied perspective. There is issue with the computationally intensive, require good exploration strategies, and learning can be slow in the complex environment. If there we have some complex environment, then we have the issue with the SEC. So in the from 3.1, we observed that the DDPs is better one as compared to both for the complex environment. Now RL SEC perform well in challenging environment with the noisy rewards, and its entropy maximization makes the exploration more effective. So SEC is good, DDPs is more good. Now Q learning is if you have the discrete action. Above 3 regarding the continuous action, but if you go with the discrete one, like we are working in the, like I have worked with the load frequency control, okay, in the past system. So I go with the DDPs, okay. Now, but whenever I go with the like discrete actions in the like converter, DAP converter, then we are going with the Q learnings. Okay, so we have done the both the things in the work. Now, so Q learning is easy to implement, effective for discrete action spaces, can guarantee convergence in the simple environment. So the issues is poor scalability with large state spaces, require discretization of the continuous space. Definitely there is a sampling time, selection is a tough task, and your samples is proper. So this is an issue with that. Sensitive to exploration strategies. So how do we can RL effective? Q learning works best for the simpler discrete action problems, but struggle in the high dimension or the continuous setting. If you have the continuous, definitely for continuous setting, we are going with the above 3.1. So it's better, you can get the better responses. Okay. Now, so DDPG, I have show you some programs regarding the RL DDPG based controller for the low frequency control. Okay. So DDPG is the actor critics algorithm that is used in the continuous action plan. It combines the benefits of the deterministic policy gradient with the Q learning, based on the Q learning, but we are not going with the discrete way. Okay, DDPG uses the critics to estimate the action value function Q based on the state and the action. Okay, and an actor to determine the policy pi based on the it is policy regarding the you're based on the state. Okay, what is your current state? Okay, so DDPG components, there is a first is actor, your policy. Now, policy act as actor. So policy gives the response to you based on your input. So actor outputs the action AT given the state, whatever the based on the your state ST according to the policy. What policy you are following? Like that, some algorithm. Okay, some fundamentals. Okay. Now pi theta ST. So where theta is represent actor network parameter. So it is what is it is nothing but the action of the your policy, the final output. So it is nothing but pi theta pi. It is policy based on the state. Okay. So your output is the AT based on the state. What is the environment state? Okay. ST is nothing but the environment state. What parameters you want to observe from the state? Okay. Now critics value function. Okay. So the critic evaluates the action taken by the actor by computing the Q value function QS. It is based on the ST and AT. Whatever the state and the action that estimate the future reward given in the given a state action pair. So whatever the rewards you get based on the your critics. Okay. So Q5 Q pi ST80 is nothing but the evolution based on the this particular function evolution, like RT is the reward at the time t plus gamma is the discount factor, and the phi 5 days 5 is nothing but the your are the parameter of critics and target critics network respective based on the next state or next action. Now, so target network to stabilize the training whatever ongoing. DDPG uses the target network for the both actor and the critics. Okay. Now, so these target networks are the updated slowly and typically using the Polyak averaging methods. It is generally used in the DDPG. So like theta days is nothing but the it is updated one is tau is a small constant theta plus 1 minus tau theta days. So theta and theta days also we can concept like that. It is critic and target critics. Okay. Now, so critic updates. Critic update nothing but the critic is updated by the minimizing the temporal difference TD error. So there is a one of the error. We need to minimize it based on the optimization, and we can get our better response. Okay. So L critics is observed from this particular equation. This one. So where target YT is nothing but the your RT reward at the current plus gamma is a function is a constant. Q 5 days ST1 plus it is based on the next state and based on the this is your pi 5 days which is we have discussed here 5 days and theta days and Q5 this is your critics value function and this is your reaction function. Okay, so based on these earlier one discussion we get your target output. So actor updates, how do we can update our actor like this function? So actor is updated using the deterministic policy gradient. We have the deterministic policy gradient base we have. So this is a gradient. We are got the gradient of the your function policies and the your Q5 function. So the update is done by the applying the deterministic policy gradient theorem, which is used to optimize the actor policy towards the maximize the Q value estimates. Based on this, we can get our rewards. Okay. Now, so based on this DDPG, we can go with that some sample coding. Just a second. So this is one of the function I have designed with the RL, and I just open it. Just a second. This is the model which is I designed. It is the running one. Just a second, it's open. People are designing the computer programming, Python's programming, but in case of the real-time models like application, there is the issues. So this is my one of the best show in the presentation. One is a conventional control, how to we can go with the RL control, RL based controller designing, and what is the benefits with the RL integration in the conventional control. And another portion, how to you can design your RL based controller for the real-time problems. Okay, so this is one of the key discussion in the presentation. So it's open. Just a second. Yeah, it's open. Yeah. So here what I have done, I have considered environment. Just I have considered load frequency control here. So if you need some load frequency control portion, we can discuss here. Don't worry. So here I have considered single area power plant. So just like the load frequency control, how the load frequency control work. So there is we have the system frequency in the India 50 hertz. So we have the power plant as the generation and we are the load at the demand. So sometimes the generation and demand is not matched. That's why the frequencies change. Okay. So we need to consider the 50 hertz, or maybe it is in the range 49.7 to 50.1. Okay, around. So it is, so we need to control the frequency. Okay. Now, so based on the this is a for multi one. So I will just show you some, just a second, how to we can get this model. Just a minute. Yeah, this is the plant. Okay, which is I will show you in the Simulink also. It is a generator, it is a turbine, it is your it is your turbine, it is generator load dynamics. Okay, with that together, this is a disturbance in the power plant. Okay, as your load demand, it is your frequency, it is your drop, and it is your controller. So it is I have considered here the RL controller here. Okay, now, so just a second. So this is your environment. Environment is nothing but the single area load frequency control system. It is your generator, it is your turbine, it is your generator load dynamics. Okay. And this is your disturbance. I have considered load disturbance here is a step function. And this is your drop. It is your drop function. And this signal too is come from the your RL controller. Okay. Like the control action. Okay. Now, so here is nothing but it is the one is nothing but the your frequency deviation in the frequency. Okay, how much deviation in the frequency? It is a df is nothing but the deviation in the frequency. Okay, from the 50 hertz. Now it goes with the observation, what is our output of the environment, just like, okay, which is I show you in the first slides also. Just a second. This one. Okay, so similar one, the our environment, we have the some state observation, there's some rewards, and then agent, then the action. Okay, we get the some action based on that. So here we have the environment. Okay, then environment got the two things. One is what is your we have the some observation here also. So output of the what environment is a state. Okay, it is state go with the RL. It is RL portion. Okay, RL agent. Okay, so RL agent have the observation portion. Another is a reward based on the some reward calculation. Okay, so reward calculation, we have the one of the objective function I have made here. Okay, based on the our control action and based on the frequency. Okay, based on it we have designed it. Now, so df based on the df we have designed it. Okay, 1 and 2 we consider here. now, and 2 is calculated whatever the controller output. Controller output is nothing but the your you as a controller output or action of the your RL. Okay, so it is action of the your policy. What policy you are uses here? So it is action. So action, and based on the observation, based on the ST or based on the your AT. Okay, we are framing the our and designing our RL agent. So RL agent continuously generate the output based on the observation and reward. Based on the observation and reward, it gives the action to our system, and based on this action, we are getting our output response. Okay, so how do we can design this RL agent? This agent. Okay, there is a key term. So this is a simple example. If you want to design the RL controller for the any type of the plant, so you can consider the plant as the environment always, and you can take the feedback, whatever the output of the system as a observation. Reward you need to design as a function, or maybe you can go with the some function, some algorithm, or maybe you can write some code here also, no issue. And there is a is done. So we have one is the is done is like the 0. Okay, no need. If you go with that, then 1 is it is opposite one that. Okay, so how do we can get the this particular values? So here we have the load system, first Simulink model. Then we have the some observation information. So I have one observation like the DF. Name and description of optional not used by the source. So we have defined as the DF as our observation part. Then control input is nothing but the U as a control action. Our output, our action of the RL. And I have considered some limits here. You can change it. For the DF is also I have considered large changes, and for the U also we have considered large changes. Now environment, how do you can define the your environment? So environment RL Simulink environment. You define the RL Simulink environment. So LFC Simulink model, LFC is your RL asset, which is we define there. Always you need to mention the things in similar perspective. Okay, this RL agent. Okay, RL agent, then you can go with the this agent. Okay, now. So there we have the define the RL agent, observation information, and the action information. Environment reset function we have here always define the reset function, always need it. So you have defined initially, randomize the value, single value you can consider here. Okay, now so observation path, action path, and the common path for that. So we have considered fully defined the feature input layers. We consider here like observation input layer, fully connected layers, and here we have the activation function is a ReLU function. We have the different function activation functions in neural network. You studied, I think. Now, so there is a ReLU is the one of the functions. So ReLU layers, fully connected layers. Now, then action path, then common path we have considered here, common layers between that. So critic network for the layers graph, like at the ear for the observation path, action path, and the common path. Then we have considered common path layers, path output layers, N1 in N1, N2 as a observation as the action path. Then we have the some plots. If you want, then I have here removes, no issue. Now critic network. Then you can go with the critic. So delnet, Dell DL network. Okay, so your deep learning network like that, critics DL networks, critic network, whatever we define above, based on it, it will define the network summary of that critics. How do you can, so RLQ value function we define here in the MATLAB also, RLQ function value, which I mentioned in the DTPs also, we use the Q function also, Q learning also. So here learning based on the Q, so Q values. Okay, so based on it, critic network, observation information, act information, observation input layer, which is we define the in the above, and the action input layers. So get the values based on the your critics. Okay, based on the dimension, what is your dimension? Then we can go with the, we have earlier defined the critics things. Okay, then we are going with the actor portion. Okay, so actor networks, we have the features input layer like observation dimension, fully connected network. Then here we have the 10 hyperbolic layers like activation function as a, now actor network we define as a DL, deep learning network. Okay, so here we have to define the actor and critics earlier one. Then we have selected here the some DDPG agents like TS 0.16 and TF is we have considered 200. You can change it as per your requirement, as per your specification. Sample time 0.1 we have considered. So RL DDPG agents we have considered actor or based on the critic or actor. So this agent will part of this one. Sorry, this one. So this agent will come here. It means the output of that. Okay, it will go with the X based on the observation reward, and it gives the action. Okay, so we have defined the agent like some base size discount factor, which is I discussed in earlier one in mathematics, and some experience buffer length, whatever you want. Now you can change it. Noise option, variance, noise option, you can decay rates, you can change it. More if you can go with some mathematics, then you can maybe consider these parameters. Now learning rate, how much, gradient threshold, how much learning rate, you can change gradient threshold also, you can change. So get the action based on the action, you get the action based on the agent and the your observations dimensions. Okay, so training option, RL training options, we have the maximum 500 episode here and maximum step per episode. It's you can consider from here. Now score, averaging, windows length. So stop condition training values is 800. Here we consider. So it gives the average reward and gives the training progress, one of the plot. So through this training, train, agent, environment, and train option, you are getting your algorithm continuously, your policy continuously updating. So whatever the results is ongoing in the simulation, it will go with the simulation also, and your output is also running. So if I will run this one, just a second, it is running. Just it takes some time. Yeah, it's running. Okay, so number of the learnables is given like that above. Okay, 1.4K inputs, one future action, definitely one. It is single output, then it's always give the response to your future number of the learnables. So it's update always. Okay, so this function is continuously updated. One more blocks will open. Just a second. Yeah, it's open. RL DDBG agent. Okay, which is mentioned in the commands also in the programming. Just a second, it is come. Yeah, come. Just a second. So we have defined the 500 like iteration. So episode number 1 is ongoing. Today's duration, how much? Final is the training in progress. You can stop it, no issue. Your episode reward, average reward, and episode initially queued node. It is also it mentioned here. So it will running here. We have the show the episode queue node also. So episode reward, episode queue node, and average reward. It will come here. Okay. So it will go with the like whatever the action you have. Okay, whatever disturbance based on it, it minimize the disturbance effect, and it go with the zero frequency deviation. Okay, DF is the 0. So then there is no issue. If again there is some disturbance will come, then this RL continuously change. So first point is come here, just like okay, another points will come slowly. It takes the time actually. Okay. It won't going, no issue. We can complete the some another more portion. Okay, so some RL control, so challenges in consideration with the RL also, some issues with the RL also. So we can discuss sample efficiency. There is a one of the issue. RL often require the many interactions with the environment, so which can be costly or the time consuming, especially in the physical systems. One of the issue. So how do you can speed up the things? Stability in safety critical application like the autonomous vehicle, it is essential to ensure that the learned policy does not result in the unsafe environment. So that's why there's a lot of maybe in at this time people are working with a safe RL. You search on the Google, maybe safe RL. So people are working with a safe RL also. Okay, generalization, the learned policy might overfit to specific training condition and may not be generalized well to unseen the states or the real world environment. So there is also issue with the generalized, but in some cases there is no issue, but in the complex cases the issue with the generalization, stability, safety, sample efficiency, and reward setting. Designing the reward function is critical. So over reward can be lead to unintended behavior. If your reward function is not proper, then you are not getting your desired response. So these are the some sort of issues with the RL. Okay. Now, so future work perspective, if I suggest you someone work in the control perspective, so from hardware implementation, performance, and robustness perspectives, researcher may work on the ADRC predicted ADRC and the RL-based predicted ADRC for the power system application. Similar perspective from the cyber physical system perspective, ADRC predicted ADRC or RL-based predicted ADRC approach can we go with the alternative solution. So if someone work with in the RL and want to work in the ADRC related or maybe control perspective, then from the real-time perspective, okay, as our desirability is the hardware maybe perspective, then you can go with the ADRC, predicted ADRC, then you can get the better wonders results for your system. Okay, so it is a thank you for your kind attention and listening the things. Hello. So this is a graph I show you like during the training. Okay, so there is a episode rewards, then this is your average reward, and this is your episode Q note initially. Okay, it is regarding the episode reward. So it go with if match the both reward average or your episode reward, then the out you can get the somehow the better responses. Okay. Hello. Hello. Hello.
Yes, sir.
Yeah. So it is from my side. If any question from the participant side, yeah, please discuss.
Participants, if you have any queries, then you can go ahead and ask. And you can put your comments in the chat section. I think so. I think so. There is no doubt. So maybe you can go ahead and start. The next.
Okay, no issue, no issue. Thank you to all participants and also organizing committee to call me and discuss my views regarding the RL and control interfacing with the participants. If anyone have any doubts, then you can email me at my email ID and mahendra@nitj.ac.in, and we can discuss the further if you are interested in the and you are stuck in the some problems. Okay, thank you.
Thank you, Mahendra sir.
Thank you, sir. Thank you. Someone have no issue.